Okay. Good morning, everyone. Welcome to the first Earthquake and Tectonics section. My name is Masato Furuya from Hokkaido University, Japan. We have today 5 talks, and each speaker is allowed to talk 15 minutes. And we don't accept any questions immediately after the talk. If you have questions or comments, please use Slido window. And also, please put @ and the speaker's name so that we can clarify to whom you are asking. And at around 13 minutes, I'll say a reminder. So now let me move on to the first speaker. The first speaker is Andy Hooper. The title is 3D high-resolution maps of intraseismic strain rate from Sentinel-1, incorporating a long-track measurements, please.
So good day, everybody. I don't yet have the option to share my screen. Oh, there we go. Thank you. Okay, are you seeing that full screen? Are you seeing my screen now?
Yeah, good.
Great, thank you. Okay, so yes, I'm going to be talking about interseismic strain rate maps today, and in particular, the importance of including a long track measurement. So the take-home message is incorporating a long track measurements hugely improves our ability to image strain. So you can see my co-authors here on the screen, but I particularly want to acknowledge Pawan, who did much of the work I'll be presenting today as part of his PhD thesis, which he handed in 3 days ago and is possibly still sleeping. Okay, so a key motivation for measuring interseismic strain is because earthquakes generally occur where the Earth is undergoing strain. And you can see that quite nicely here in this figure. So on the left is plotted interseismic strain. So this comes from California, where there's a really dense network of GNSS. And on the right, you can see total seismic moment. And overall, there's a good correlation. It's not exact, and a big part of the reason for that is we don't have a full seismic catalog covering the whole, to get a good average of where the seismic moment is. And this is where actually measuring seismic strain can really help to improve our measurements of or our estimates of seismic hazard. In terms of the kind of accuracy we'd like to reach, if we can get down to 10 nanostrain per year, so that's 10 to the -8 strain per year, then we can catch most of the regions where there are earthquakes that cause most of the fatalities. So 96% of all fatalities are in areas of 10 nanostrain or more. So that's kind of a target we have. So within the Comet organization in the UK, we've been developing a system to try and do this on a large scale. And the steps in brief are, first of all, to make a whole load of interferograms over straining regions. So I think we have upwards of 500,000 or so interferograms now on the Comet network, which are all freely available, by the way. We then invert each of the frames that we make to get line of sight velocities. We reference these to the GNSS that we have for the area, and then we combine the INSAR and GNSS together to get velocity fields and strain rate maps for these large areas. And then the final step, of course, is to incorporate these into improving estimates of seismic hazard. So you can see Tim's talk later on today for an overview of this whole system, and there are a whole plethora of other talks that Tim can point you to, where people talk about specific parts of the system and different regions. Okay, but so as we all know, INSAR only gives us the line of sight component, and if we take ascending and descending orbits, we have a good sensitivity to east-west, but very little sensitivity to north-south motion. But this means we can image strain very well in areas where the shear zones are essentially east-west. because the sort of high frequency north-south motion that we aim to pick up with the INSAR is relatively small, so we can just fill in the north-south from GNSS pretty well. And that's nicely demonstrated for Anatolia, where you can see the strain localization on the North Anatolian fault shows up really well, and also and towards the southeast there you can see localization on the East Anatolian fault as well. So for some regions this already works really nicely. But how does it do if we have a north-south shear zone? Well, this is just a simulation, but so on the left we've simulated strain. So this is just a simple buried dislocation model. So we imagine a fault stuck from the surface down to 10 kilometers and then freely slipping beneath that. And we just have a sparse GNSS network shown in this figure on the right. We try to retrieve this strain. We do a really poor job, and that's not that surprising because of the sparsity of the network. If we add in INSAR, so line of sight INSAR, and you can see both an ascending frame and a descending frame shown in the simulation, even in the area where we have good overlap of those two frames, we don't actually really improve our strain rate estimates very well at all. And again, that's not surprising because we know there's very little sensitivity to the direction of movement in this case from the INSAR, so it doesn't really help. Of course, because of the TOPS mode that Sentinel-1 has, we do actually have sensitivity in the north-south direction or the long track direction, and particularly in the burst overlap areas. So these are areas where the same part of the ground is imaged by two or more different look directions, so we can actually get some sensitivity in the north-south direction. These measurements are noisier than INSAR measurements, but when we have large deformation, it works really nicely. One of the earliest examples of this was for the Iapel earthquake in Chile, which of course had lots of motion, tens of centimeters, and you can see there in the long track motion is picked up nice in the burst overlap areas. So we developed a time series approach to try and get at the more subtle movements in the long track direction, but which are nevertheless more or less steady state in time. And this figure here is just to show you what we would expect the precision to be. So the black line there is showing the theoretical precision, and then there are three colored lines which all kind of overlap each other, so maybe they're not that clear. And this is what we actually get when we estimate the standard error from our data. So we kind of track the theoretical precision for low coherence. Our precision is slightly worse than we would predict at higher coherence, but nevertheless still in the order of a few millimeters per year. So that all sounds great. The problem is actually the ionosphere. So we're still left with a lot of spatially correlated noise from the ionosphere. Now, of course, there are approaches to try and correct the ionospheric phase signal, and we've taken the split spectrum in range method, and we've adapted it a little bit for a time series approach, so we can improve a little bit by treating a whole time series together rather than individual interferograms. And we've also done some work on the filtering that needs to be done within that to try and improve some of the edge effects you get in areas of low coherence. So you can just see an example of that shown in this figure on the two figures on the right here. So by filtering slightly better and doing the time series approach, we can get better results. So we can reduce this ionospheric noise somewhat. So I want to show you an example now. This is the West Lut fault in eastern Iran, and it's pretty much a north-south strike fault. The GNSS that I'm showing here are, well, hopefully you can see there's a slight gradient in the north-south motion going across the fault of a few millimeters per year. And if we look at the ascending line of sight results, we do see deformation associated with earthquakes and subsidence, but across the fault, essentially, we see no gradient, and that's to be expected because of the line of sight direction. Okay, well, these are our long track results, and you can see they are still noisy. This is mostly due to the residual ionospheric signal. Even though we've done some corrections, there is still some noise there, but hopefully you can see there is a kind of gradient going from the west to the east as a gradient in color. And we can see this even better if we do some averaging. So if we take 9 burst overlap areas, and average in the sort of fault parallel direction, which is north-south here, we get this, and now it becomes more apparent that there is a step in velocity from going from west to east. So taking these same data now, so now showing them as blue points, these are the long track measurements. I'm also showing here the GNSS results projected onto this, this profile, which is shown as black squares with error bars. So you can see there's good agreement overall between the INSAR and the GNSS. We can use both either separately or together to estimate the slip rate using, again, a simple buried dislocation model. And we get similar slip rates if we use just the GNSS alone or the INSAR alone, sorry, the long track alone, or together. But actually having the density of measurements from INSAR allows us to constrain lock-in depth, which is actually pretty difficult to do with the GNSS alone. If we look further south on this fault, you probably see that actually there's a bigger gradient, bigger step in velocity across the fault. And that's likely because some of the strain further north is taken up by the Kubernetes fault. But we can do the same trick again and average along the fault. And because the slip rate is higher in this region, it's approximately double, you can see much more clearly this change velocity, and also it fits very nicely with a simple model of a buried dislocation. Okay, in that area, unfortunately, the descending data well, there's a problem with the descending data because there's a lot of noise, a lot of interference on the ground from presumably from military radars, and we haven't tried to deal with that yet. But I'm going to show you another area here where we have ascending and descending data. So this is the Shaman fault in the Pakistan-Afghanistan region. So now I'm showing just for one profile in these 4 panels on the right, the ascending and descending tracks, and then you've got line of sight at the top and the long track at the bottom. So most of these show some sort of step across the fault because it's not exactly a north-south fault in this region. But if we have all 4 of these measurements, we can, of course, then decompose and estimate the 3D velocities. So this is now showing easting, northing, and vertical. And of course, because the accuracies and the precisions we get from the long track are not as good as the line of sight, there is some different variation in the scatter you're seeing here. But we can also, of course, project into the fault parallel direction using all 4 line of sights and along tracks. And that's shown in the bottom right here. This is the fault parallel velocity. And again, it shows something similar to what I was showing before. In this case, a slip rate of 10 or so millimeters per year. Okay, so that was just a couple of case studies. How does it improve with our overall goal of imaging strain rates in all straining regions? Well, this is the figure I showed you before. So this was just a simulation of strain rate, and we just use GNSS and line of sight alone. We can't do a very good job. If we now add in these along track measurements from both the ascending and descending geometry, you can see that actually we do pretty good job of identifying where the strain is localized. We don't quite get the magnitude. That's partly due to the coarseness of the mesh, and it's partly due to the accuracy of the measurements. But in terms of localization of the strain, it does work quite nicely. So one other kind of nice feature of these long track measurements is, unlike INSAR, they're not relative measurements. They come in a global reference frame, which is ITRF. So what we've done is we've taken all our interferograms we've generated in the comet system, and we've estimated for each frame the average along track velocity. So for every frame, we have a figure like this one on the left, which shows the time along the x-axis and the azimuth shift in the y-axis. So the red points are the kind of the raw measurements. Then we've corrected for tides, and we've corrected for the ionosphere, in this case using tech maps, and that gives you the green points, and then we can calculate an average velocity, and that's what's shown in this panel on the right. We could compare this to ITRF. So these are kind of what we would expect to get for the
2 minutes left.
Thank you. I'm almost done. And yeah, what you can see overall, there's a very nice correlation between the two. So our data are actually matching RTRF very nicely. So just to reinforce the point, these are just direct measurements. We haven't had to do any re-referencing or anything like that. These are just what comes out of the estimating the long track motions given the orbits data. And it works for descending too. This is a zoom in on the Alpine Himalayan region. And again, you can see a good correspondence between the two. So some of the differences between the data and the ITRF will be due to noise, but some will be real, of course. ITRF is a simplified model of plate motion, and we know that it's more complicated in these regions of collision. So I encourage you to look at Milan's poster. He gave us on Tuesday, but of course it's still available. I hope it's still available to take a look at. So our aim is, and we haven't done this, is to incorporate our long track velocities into our sort of overall approach. So we have to insert it in step 2, where we actually calculate the long track velocities, and then again in step 4 we have to actually include it in the inversions as well. And we hope, or we know, this will improve in many areas our estimates. So that's it. Just to conclude then, the take-home message here really is that by including these long track measurements in our strain rate estimations, we can really improve our estimates in areas where we have significant north-south motion. So thank you very much.
Thank you, Andy. Okay, so the next talk is given by Yohai again. And the title is Reconditioning Slip Inversions via Downsampling of INSA Data. Examples from the Lagula 2009 and Ridgecrest 2019 earthquakes, please.
Yeah. Hi, everyone. Okay, so I'm going to propose a new approach to increasing the stability of the inversion problem, or decreasing the effects of errors in the data on the inversion problem, and this will be done. This will be done via reconditioning of the slip inversion, and I will show 2 case studies, one of the Lagula, Italy 2009 earthquake, and now and the second, the 2019 Ridgecrest, California earthquake pair. So we will start with some motivation. So in general, errors in our data are mapped to the model space by the generalized inverse of G, of our elastic kernel. And the elastic kernel is a function of our fault geometry and the discretization of the fault plane and the data space. And by discretization of the data space, I mean what approach of downsampling we are taking, because no one that I know of using the whole INSA data set in the inversion problem. We're taking some kind of downsampling approach to take it from few millions of data points to a few thousand of data points. So if we're looking on a very simplistic synthetic model with the plus slip pattern, and we're computing unwrapped synthetic insert image, and then we're calculating the generalized inverse and applying it on the data, we're not surprisingly will get almost perfectly the same slip model that we started with. And this is not a surprising result, because we calculated the data with the same elastic kernel as we inverted it with. But if we're adding some errors to our data, do not need to be very large, we're suddenly getting a different result. We may keep some of the same features. The maximum slip is still in the same place, but a part of that we're getting a pretty different slip pattern. One approach of dealing with that problem is adding some smoothing constraint to our slip model. Indeed, adding smoothing constraint making the inversion very stable, and is not affected almost by adding noise to the data, but adding a smoothing constraint, and by adding smoothing constraint, we taking an assumption that our sleep model is smooth. This assumption does not necessarily hold. It's debatable, and at least in the very simplistic synthetic model that we show here with the plus sign, we do get much better results than not regulating at all our inversion problem, but we have some leakage of the sleep model from the plus outside of the plus. So we will define the inversion condition number, and we will try to optimize it. So the generalized inverse of the elastic kernel is computed by the singular value decomposition of the elastic kernel. Singular value decomposition decompose the elastic kernel to three matrices, U, sigma, and V, where U and V are orthonormal matrices that span the model and the data space, and sigma is a pseudo-diagonal matrix with the singular values on its diagonal. And we can see that the data arrows are mapped to our model along the vectors of U and V, which does not impact the size of the arrows because they are orthonormal, they are unit length, and they are stretched by the inverse of the singular values. So having very small singular values can lead to very small errors in our data, become very large errors in our model. So we will define the condition number of the inverse problem to be the division of the largest by the smallest singular value. And by keeping this condition number small via discretization of the fault of the model space and the data space, we will promise that we will not have small singular value and we will have a stable problem. So our first case study will be the Lagula 2008 earthquake, which occurred in the central Italy in the Apennines, right next to the Lagula city. And we will use actually the same fault geometry and the same data as Guerri 2010, other model done to that earthquake, in sake of comparison. So we will have two fault plane dipping at 45 degrees to the south west that we can see here in the red polygons. And all the yellow dots are the precisely relocated aftershock sequence of the Lagula sequence. And we will use them later in order to validate our sleep model. So our data set is composed or processed from the European Space Agency and the satellite, and we have an ascending and descending track. And as I mentioned, is actually exactly the same data set that was used in Guerri 2010. Thanks to Gidi Ber, who was very organized in saving 10 years old data sets. And we can see in the descending track the classical normal faulting pattern of subsiding globe and rising globe. And we will propose two configurations of discretization for the fault plane and the data downsampling, where the first configuration using depth-dependent fault plane discretization, where dislocation getting larger with depth to account for the loss of resolution. And in the data space, we're using maybe the most common and widely used downsampling approach, where we're downsampling the data according to the displacement variance. And we're trying to end up with a uniform variance data. And our second configuration will be discretization, where we optimize, essentially by iterative process, optimizing the condition number and keeping it small. I will mention that also here we are getting a depth-dependent fault plane. We didn't start with a depth-dependent, we started with a uniform fault plane, and that's part of the process. So optimizing the condition number, also accounting for the resolution of the inverse problem. And we're finishing with a condition number which is 2 orders of a magnitude smaller than the first configuration. We will finish this part by showing the slip distribution, where on the left we can see our new slip distribution, and to the right we can see Guerri et al. Slip distribution. Because we're regulating our inversion problem by optimizing the condition number, we can use much smaller smoothing coefficient. I do not know what was the smoothing coefficient of Guerri et al., but to get about the same result, I need to use 0.1 smoothing coefficient, where we used 10 to the minus 4 smoothing coefficient, so much smaller. And we do get nicely the aftershock sequence of the Lagula earthquake in the 48 hours following the main shock, wrapping the slipping dislocation. So the aftershock occurring where the shear stress due to the main shock is maximum, where in the other slip model, actually the most of the aftershock will occur where we have a decrease in the shear stress due to the main shock. I will now move to talk about our second case study, which will be the Ridgecrest earthquake sequence, or the Ridgecrest earthquake pair. And here on the left, we can see the fault geometry that was involved in the sequence, where we can see the seismicity pattern of, the sequence was composed of a pair of earthquake, a foreshock in the 4th of July 2019, and a main shock that occurred 34 hours later. And on the left, we can see the seismicity pattern of both the foreshock and the main shock. The foreshock in cyan and the main shock in red colors. And from the seismicity pattern itself, we can say that probably the main shock ruptured mainly or only the northwest striking fault. But we cannot say, not from the seismicity pattern and not from the moment tensor solution, of course, which one of the faults has been ruptured during the foreshock because of this nice orthogonal seismicity pattern. And we will try to resolve it with some geodetic slip inversion. So our prime data set will be Sentinel INSAR data, where we have a descending and ascending track, which give us very nicely INSAR images. But the problem with INSAR data in that specific sequence case is no SAR satellite had a pass above the Ridgecrest area between the two earthquakes. So all the available INSAR data containing the superposition of the displacement of the two earthquakes. So we cannot use INSAR data alone in order to distinctly resolve the slip of the foreshock and understand which one of the fault has been ruptured during the foreshock. So our inversion scheme will include two additional data sets, GPS displacement and optical imagery offset displacement, where both the INSAR, the optical imagery offset, as the fault geometry, discretization was optimized via the reconditioning process. Our inversion scheme will solve for both the main shock and the foreshock at the same time, essentially in order to use the INSAR data. As I mentioned, it contains a superposition of the deformation. So the INSAR data will be accounted for the slip of both the main shock and the foreshock, where the GPS and the optical offset will be accounted to distinct between the two events slip. We end up with the following slip model, where in the lower panel we can see the slip model of the main shock, and in the upper panels we can see the slip model of the foreshock, where on the left we're looking on the fault from north to south, and on the right we're looking on the fault from south to north. Not surprisingly, as I said, in the foreshock we resolved that 98% of the moment.
2 minutes left.
Thank you. I am finishing in 2 minutes, no problem. 98% of the moment has been released on the northwest striking fault. But in the foreshock, we're getting much more interesting picture where the moment is released about half and half, 60 to 40% between the northwest and the northeast striking fault, where the northwest striking fault is slip at depth in the intersection point between the two faults. And more interestingly, this asperity, we named asperity 2, slipped twice, one during the foreshock and one during the main shock 34 hours later. It actually slipped 4 times as much. So we need, for that to happen, we need to consider some fast healing processes to the fault plane. We will finish with showing the Coulomb failure function due to the foreshock slip. We're getting a 1.5 megapascal increase in the Coulomb failure function in the initiation point of the main shock, where 90% of that Coulomb failure function increase is due to the shear stress increase. And the shear stress increase is mainly or only because of the slip on the same fault. So without slip on the same fault, on asperity 2, we would have much smaller promotion in the direction of failure on the location of the main fault. So I will summarize. We showed a new model and data discretization approach in order to improve the stability of the inverse problem. We show a slip distribution of the Ridgecrest earthquake pair, where we had an asperities that slipped twice in 34 hours and increased the shear stress on the main shock initiation point. Thank you.
Thank you, Yohai. Okay, so the third talk is given by Henriette Sudhaus, and the title of our talk is Simultaneous Joint Optimization of Two Ruptures of the 2012 Ahar Earthquake Doublet, MW 6.4 and 6.3, Iran. Please.
Yeah. Thank you very much. So I'm just setting up the slide share. So good morning from Central Europe. I'm hired here in Berlin. So then my problem starting. This seems to take a minute. Okay, so what my presentation will be about is imperfect continuation, actually, from the previous talk, is that we deal with earthquake doublets. So an earthquake doublet are two earthquakes that appear very close in time and space and are of similar size. And so for this, we know that INSA does not have the temporal resolution often. So to distinguish between these two earthquakes, you need to basically build a bridge to get in more data sets, and this will be in this presentation as seismology. When the slideshow would, it says connecting. I don't know why. Maybe I will just stop for a minute my video. Apologies, but maybe this helps with the connection. Actually, it does not. Yeah, I'm very sorry. I tried to send also slides ahead, but somehow they are corrupted.
Can I intervene? Excuse me to the panel. This is Sabrina from the organizing committee. I'm trying to sending the presentation to the technical person. Andre, could you please display the slide on behalf of Henriette, because also from here we have problems.
Yes, okay. Where did you send it?
Can you send me your email address, please, Andre? So you paste in the chat, please. Thank you very much. Sorry, Henriette, for the problem.
Well, I'm sorry. Somehow my system does not, I don't know, does not like WebEx. I don't like WebEx either. So, so maybe I would like to acknowledge my co-authors. So we have Stefanie Donner and Abdul-Reza Gotz from Iran, seismologists who have been doing a lot of previous work actually on this earthquake doublet. And since I stepped in with the inside data, they're basically waiting for new results with this joint optimization.
Looks good.
Yeah, it looks good, but I need the first slide maybe.
Okay.
Thank you very much. Oh, this looks good. I'm relieved. Yeah, and then there's Andreas Steinberg and Jan Ridderbusch who have been working in Kiel on this earthquake. So thanks a lot for your patience. Next slide, please. So this will, next slide. So while this will be a rather problem-oriented presentation, of course, we need to look where we are. So this is an earthquake doublet. It could be something like the Ridgecrest earthquake, or it could be something like the Greece sequence that we had in the beginning of the year. Because also there, with INSA, we often have like two similar sized earthquakes within one interferogram. Here we are in the northwest of Iran, and the earthquake doublet appeared where the black star is, relatively in the middle of the plot. And this is a region of, northwest Iran is converging towards Eurasia, and we have a slight bend in these GNSS vectors at the North Tabriz Fault, NTF called here. So for this earthquake doublet, we had less separation than for Greece or Ridgecrest. We have just been 11 minutes of separation between two earthquakes. And this poses actually already for seismology also a problem, because wave trains of P waves of the second earthquake and S waves of the first one will also run into each other at teleseismic distances. So what you can see here in blue triangles are regional stations that we got from Iran, and they help us to disentangle these two sources using seismology. Next slide, please. What you can see here is the whole seismic sequence for several months after these two earthquakes. The first one is the lighter bluish earthquake, strike-slip earthquake Dextral. And the second earthquake is the largest one, the largest beach ball that you see in purple. And you can see that they have also, from seismology, they look like they have different mechanisms, and they're also a bit differently located. You can see that there has been a surface rupture mapped in the field. This is has also been seen in optical data. Yeah, the question is now really how this, yeah, if we can do better, if we put together INSA and seismology. Next slide, please. So, of course, I would like to show you fringes. For this earthquake, it happened in 2012. So there was no ERS anymore. There was no Envisat anymore. There was no ALOS-1. Yeah, and the new satellites have not been there. So for C-band, for instance, we just had RadarSat. And I was lucky to get RadarSat data via ESA SOAR-2 project. And unfortunately, there's only ascending acquisition. So this is also, this just one look direction. We are missing dimensions. And you can see that we also lose quite some coherence in the near field of the earthquake. This interferogram spans several months from April to September. So from the inside of things, this is also not perfect. Next slide, please. So what I'm showing you now is legacy slides, actually, from Fringe 2015. I have been 6 years ago already here showing you work on this earthquake doublet. But I did the usual thing, let's say. So I took an Okada dislocation, homogeneous elastic half space, and modeled the earthquakes using just this ascending interferogram. I added, to have some like 3D deformation, I added one GNSS station that you can see with the white arrow, which is placed in the town of Aha. So when you just model like for the first source and see if this is already a good fit, you can see that you managed to quite well explain the interferogram, the displacement with a single source that arrives perfectly at the mapped surface trace, which is in the middle. You can see it in red in the middle panel in the modeled one. Yeah, you have some residuals. So the question was, do we have actually sensitivity for the second earthquake? Seismology says it's a bit deeper. Next slide, please. And so I did a simultaneous optimization of these two earthquake sources in the same, with this interferogram and the GPS data. I'm not sure if the next slide is just lagging. Thank you. So here you can see you can see that you have some very nice constrained parameters for the first earthquake. This is the first row of histograms. I'm not going into the details, but on the second row, you can see that, we improve with two sources. We improve the fit, but there's some parameters that are not well constrained. So I would like to point to depth. This is the third column. You can see that the source tries to vanish basically to deeper depth where we actually lose the sensitivity, and you can see that it adapts for this by increasing the slip. Yeah, this is on the rightmost panels and the lower histograms. So yeah, it's a bit difficult just from surface data to get a grasp. So what I left you with in 2015 was that still what we got from these optimizations is that seismology and geodesy, they kind of agree. So this is nice, and INSA seems to be able to constrain something. Please, next slide. But of course, you would need to make a true joint optimization. Okay, next slide. And this is where we are now, 6 years later. I wanted it to be like 5 years later, you all know. So what we now do is we combine seismological data and geodetic data. And I often try to put this in a near field perspective and far field perspective. So when we are in a near field, our displacement, the static displacement that we measure with low rate GNSS and INSAR is proportional to the moment of the earthquake. Yeah, so this scales. In the far field, however, the seismic wave of the moment, but it's proportional to moment rate. So what we need is actually a source that has a rupture speed, a dislocation speed. Next slide, please. And so our source cannot be an Okada source anymore, but it needs to be a rupture, right, with a nucleation and with a rupture speed. Next slide, please. And you cannot forward model seismic waveforms without having a proper velocity model. So we needed also a layered half space as well. Next slide, please. So this is basically what we do. We have a rupture, a finite rupture source with a nucleation point, and we embed this in a layered elastic half space. We use what you've seen on the previous one on the previous slide was that you have for the local region, you have a different velocity model than for the global one. So there's still some inconsistency, but we're getting closer. Yeah, let's say. So so the joint data set, we added GNSS data. So we not just have the AHA station, but we used GNSS vectors published by Yadav et al. 2016. And what you can see is the quarterly subsampled displacements of the interferogram I've shown before. And you see also the mapped surface trace. Next slide, please. So, and these are the seismic stations that we're using, regional stations up to 1,000 kilometers from Iran. This is in the southeast. So the station in the southeast on the upper polar plot. And then we have also Turkish stations. The azimuthal distribution is not perfect. And then we also have teleseismic stations. So basically global stations of the seismic network. Next slide, please. So I'm coming directly to the model results, and this is the best model of this earthquake doublet. It's a surface projection. You can see that, again, the first So the first main shock arrives directly at the mapped surface trace, even though we didn't force that, so that was free. And the second source, sits south of that with a dip to the north, and as also is an oblique strike slip mechanism. But that's just the best model. It fits the GPS data well. It also fits INSAT data well. But this is not all. So next slide, please. We have to remember that we do an optimization with a randomized and then optimized procedure. So this is similar to Bayesian. It is actually a Bayesian inference also of the sources. And what I'm showing you here is likely models of the first shock, and you can see that they concentrate very well on the point where we have seen the first earthquake solution. For the second source, it's not that simple. Next slide, please. So thank you. So what we see here is some back projection results. So this is something completely independent. So we're using seismic waveforms and project the energy back to the source. And these are results provided by Andreas Steinberg. He is with us, so you can contact him if you want to know the details. And what you see here is that the rupture seemed to have started in the east and then propagated westward. And also these seismic results fit very nicely to our source locations. Next slide, please. For the second source, things look different by means of it looks much more fuzzy. So convergence is not as good, and we see that we have kind of a bimodal distribution of the solutions. We have something more east-west oriented. So I'm showing just the upper edge outlines here to make it that we can grasp the information. It's not just all black. And we have quite a bunch of models that have more north-south striking direction. So this fits to mechanisms like dextral or sinistral mechanisms. So this is all fine. It's just something that we cannot really well resolve. And this is maybe something that we have to live with. Next slide, please. So here I'm showing just a few of the parameter histograms for these locations for this source solution. And in particular, I would like to point you to the depth. This is in the middle left panel of the histograms. So with the seismology, we can better constrain the depth than we could before with INSA only. We have we have a bimodal distribution, which I think also from the kinematic modeling of the seismology is just it's just like that. So if we would provide this to an earthquake catalog, I think we would provide this ensemble and say, well, this earthquake happened at a deeper level than the first one. So these are the possibilities for the mechanism. I would like to add here also the back projection results. Next slide, please. I hope this is visible. So if you look on the back projection results, it looks like this earthquake propagated from north to south, and then there's also some energy in the north again. So if we take these additional results, then it looks like the north-south planes are more probable. Yeah, but this is extra information which you can use. So with this, actually, I'm at the end. I would like to add maybe that first of all, you can use the QR code to look at the detailed results with all the parameters that we optimized for this case, and also some other earthquakes if you're interested. And well, it took me 5 years, or us, to arrive there with Andreas and Jan and my co-authors. But this is actually an open software code. So this doublet optimization is something that we have in a developing stage, but we hope to have this ready to use for everyone within the year. So check out pyroco.org. This is just at the lower left written. You can do this at home. Thank you very much.
Thank you, Enrique. So let me move on to the fourth talk. The title is Improving the Resolving Power of INSA for Earthquakes Using Time Series, a case study in Iran. And the talk is given by Fei Liu. Please.
Can you see my full screen?
Yes.
Okay. Hi, everyone. I'm Fei, a PhD student from University of Leeds. Today, I'm going to talk about improving the resolving power of INSAR for earthquake using time series. It's a case study in Iran. With the advance of INSAR mission, INSAR has become an established method to measure the Earth surface deformation caused by earthquakes. INSAR provides an alternative approach other than seismology to provide the measurement of source location, depth, and orientation. However, due to the dominant error sources within INSAR data of atmospheric and decorrelation noise, that earthquake only above a certain size or that shallow enough can be observed. Recent study using single co-seismic interferon to detect earthquake for the first instance. However, this approach is inconsistent, not robust, and subject to high failure rates. Here shows the example of earthquake detection by single interferon. Panel A shows the detected case. Panel B is the ambiguous case, as it's hard to say whether it is associated with the deformation signal or just pure noise. And panel C is totally decorrelated, and we can't see any useful information. These circumstances make INSAR for earthquake study challenging. So our first primary motivation is to increase the chance to observe and study earthquake by INSAR, especially for small earthquakes, as this earthquake can still cause many fatalities when close to the population center, despite their relatively weak signals. Secondly, due to the poor constraint of precise location of seismology in the region of low instrumentation, we want to locate this earthquake using INSAR. And by precisely locating the small earthquakes, it may be possible to link seismic activity direct with active fault structure that are capable of larger earthquake. Furthermore, we may draw inference from a huge number of small earthquakes, assuming their behavior scale similarity with the larger ones. So to fully explore the potential of INSAR detecting earthquakes, we perform INSAR time series as its crew can extract co-seismic signal from various sources of noise. The study area we choose is southwestern Iran. On 2017, a large 7.3 earthquake started this region, triggering a lonely seismic deformation, and later many aftershocks that are suitable for our study. We have processed 5 years of Sentinel-1 observation from 2014 to 2019 to ensure enough data is available to constrain any potential secular or annual deformation, such as the seasonal term. As shown in this figure, the red star here indicates the epicenter of the main shock, and the gray circles are the aftershock whose magnitude above 5 from the USGS catalog. Red line are the main active faults, and the white and black dashed rectangle shows the covering the area of Sentinel observation for both ascending and descending tracks. Here we focus on 3 late aftershocks indicated by the red focal mechanism, magnitude ranging from 5.6 to 6.3. The first thing we want to show here is how time series improve the earthquake detectability. The main panel here shows the shortest temporary baseline of the single interferon for this 6.3 earthquake, and the other 3 smaller panels shows the longer temporal baseline of the deformation area marked by the dashed rectangle. All this interferon has been corrected by geckos to remove the tropospheric noise. As we can see here, this is already visible earthquake on single interferon. Accordingly, we can observe the co-seismic offset for this peak displacement pixel P1. The event time is indicated by this blue vertical dash line. And to help illustrate the co-seismic offset, we fed the data with a simple step function, which is shown by the red horizontal line, and the error bar is showing the uncertainty of the co-seismic phase. However, when the earthquake signal is marked by strong atmospheric noise, as shown in the case for this 5.6 earthquake, this is ambiguous case, as the deformation signal are not quiet enough that are completely invisible on the examination of multiple interferons. While on time series, we confidently observe the co-seismic offset as the event time is indicated by this green dash line. An interesting point here is that actually these two earthquakes happened coincidentally in time with only 7 observation gap, and we confidently determine their co-seismic offset on time series. Here is our workflow. The black arrows here indicate the preliminary routine of using single interferogram to do earthquake modeling, while the white arrow shows our time series approach. Compared to single interferogram, the most important part is inside time series can frequently estimate the surface displacement, so that we can use a time-dependent model fitting appropriate for the displacement due to the seismic circle, and then reconstruct the co-seismic deformation fields, and use this Nash-Neuer reconstruct deformation field to earthquake modeling, and later compare to seismology. This is the model we used in our study. Here, H is a step function. T1 delays the event time of the main shock. C1 is the co-seismic offset, and we use a logarithm function to represent the post-seismic decay. As for the 3 aftershocks, we model them together as they occur coincidentally in time, as shown in previous slides. Whilst the post-seismic deformation may follow all earthquakes. Here we only consider the dominant post-seismic deformation from the 7.3 main shock, as these 3 late aftershocks are either small in magnitude or occur too close in time and space, impeding robots post-seismic fitting. Although this simplification will lead some early post-seismic motion into the reconstruct deformation field, the later instar-derived magnitude and moment is consistent with the seismological data, illustrating this effect is limited in these cases. And the V here, represent the long-term linear rate, which contain in part the interseismic rate. My colleague Andrew will give a talk this afternoon about using INSAR to measure the interseismic within this region. And B represent the constant offset. We apply gap cost correction to all interferograms, which greatly reduce the standard deviation of the fitting by 24% and suppress the seasonal term. Here shows the example of the 6.0 earthquake on 3 different tracks of the time of the data fitting. The left hello shows the reconstructed deformation fields, and the red ones are some peak displacement pixel fitting. We first observe the large co-seismic offset by the main shock, the post-seismic decay, and then the 6.0 earthquake indicated by this green dashed line. So to compare the single interferogram to our reconstructed deformation fields, we first show the forward modeling of 3 earthquakes on ascending track using the fault parameters from the USGIS. This is the ideal deformation pattern from the prediction of seismological data. Then we compare the shortest temporary single interferogram with our reconstructed deformation field. We can see that the deformation signals are less noisy and easily recognizable after reconstruction, especially for this 5.6 earthquake, which is masked by strong atmosphere in single noise, but are resolved after reconstruction. We later used the GBS software to do the earthquake modeling. The minor residues between the input reconstructing deformation field and the output modeling validate the effectiveness of our approach. We quantified the signal to noise ratio improvement after reconstruction. Errors in INSAR data can be simulated using an exponential function fitted to the semi-variogram. We mask out the deformation error and remove a linear ramp before the fitting to indicate the noise reduction in the far field. Here shows the fitting result of the single interferogram, and our the blue and red line represent the fitting result of the single interferogram and from our reconstructed deformation fields respectively. The fitting seal value, which represent the approximate maximum value of the fitting curve, represent the noise level. The lower seal value, the higher the signal to noise ratio. Therefore, we can see after reconstruction, the signal to noise ratio have improved for earthquake in different tracks. The more important advantage, the more significant advantages come from the better constrained earthquake modeling. We use the GBS software to do earthquake modeling, which is implemented by a Bayesian approach, providing not only the optimal solution, but also the posterior distribution of the solving results. Here shows the modeling output of the 6.0 earthquake, for example. And the blue solid line and the beans represent the optimal solution and the posterior distribution from the single diaphragm, while the red of those are from our reconstructed formation fields. The much narrower posterior distribution from our reconstructed deformation fields suggests a better constraint for parameter from our approach. And for this 6.0 earthquake, as the deformation signal are more distinct after reconstruction, it achieved an average of 56% confidence interval reduction for all parameters. And combine the results from other two earthquakes, in total, we achieve a 36% confidence reduction. Finally, we compare our results to the seismological observation. In summary, except few discrepancies, our inside-derived results agree well with the seismological data, especially using our transparencies approach. Here, we focus on the comparison of the location and the central depths, where it shows the advantage of inside observation. The upper figure shows the location from different sources. The star, black rectangle, and background deformation pattern are the source location for plane projection on surface and the modeling result from our reconstructed deformation field. The circle here shows the source location from a recent inside-derived solution, which agree well with our results. And the other symbols indicate different seismological observation from different catalogs. Note for this 5.6 earthquake, which is not modeled in phasing study, and ISA epicenter from this earthquake is not yet available. While the central depths of the earthquake, routine measurements from the seismology data probably contain value fixed period, such as the 10-kilometer depth here for the 6.0 earthquake from the USGS. Overall, our INSAR data achieve a shallower depth measurement. Also, the true value of location and central depths cannot be known without near field constraint from such as dense aftershock survey. From the deformation pattern shown here, we believe INSAR provide better constraint for location and more informative depth information. So in conclusion, here we demonstrate the use of INSAR time series to detect and model aftershocks in the presence of the post-seismic deformation following a major earthquakes. We developed an approach that using time series to enhance the space angle and subsequent better constrain the earthquake modeling. As for the implication of our method, the primary use of our approach is to improve the INSAR detectability, such as very small earthquake magnitude below 5 when it reaches to the Earth's surface. And it also can be used to enhance complex signals and distinguish early post-seismic motion to from the seismic offset due to the latency of sound acquisition. Further applications of our research, our method can be used to split complex sequence of earthquakes, especially aftershock sequence, as we have done here, or study small magnitude signals from large deep earthquake within subduction zone. Our work has been submitted to JRL and should be available soon. Thanks for listening. I'm happy to answer any questions.
Thank you, Fei. Okay, so now let me move on to the final talk given by Fernando Monterosso. The title of his talk is A Fully Automatic Global Database of Sentinel-1 Co-Seismic Interference within Cloud Computing Environment. Please.
Yes, please. Can you enable the option for the share my screen, please? Because I don't have here. Thank you. Okay, can you see here on my screen?
Not yet in full screen. Yeah, good.
Okay, perfect. Thank you. Good morning, everyone. My name is Fernando Monterroso from IREA CNR. I will introduce the full automatic global database of Sentinel-1 consistent interferograms within the cloud computing environment. Okay, the outline of my presentation is the first one. I will introduce in general way how it's possible to apply the student earthquakes with DINSAR. I will talk about the Sentinel-1 constellation and its constellation that I am using for processing all the automatic way interference along displacement maps. And I will talk about a little bit way on the parallel Sentinel-1 DINSAR workflow that is an algorithm that I'm using. The core of this presentation, let me say, I will speak about to do the automatic generation of cosmic displacement maps by using the Sentinel-1 interferometric source data. This is the core of this presentation, how it's possible to generate in an automatic way the interference allow displacement map input for the service with geophysical, personal, and also sphere protection way. And after, I will explain in general way and also how it's possible to integrate all these automatic tools in implementation in cloud computing facilities, and specifically on Amazon Web Service. And after, I will show you some interesting results and conclusion on this research. So, in general way, we can start to explain and we can start talk about the Landers earthquake. Let's say in 1992, the last 20 years, when I'm using interference for earthquake studying around the world. In this case, this is the portal of magazine Nature, and you can see here the first interference generate 22 interferometric pairs. In this case, here's one images. This is the first application of DINSAR technique on the earthquake. So started from this way, we can let's talk about to do this technique is applied directly for the study of earthquakes in general way. So in the state of art, about to the studying earthquakes with DINSAR, the historical review, we can see here more or less we have a lot of possibilities for generate or a lot of images for generate this kind of maps that represent the formation area. Started in 1992, we can see here the different interferometers generated with MBSAT for ERS1, for Cosmos SkyMed, and also in this case for Lagula earthquake and Italy and RadarSat-2 and Aldous Palsat and also for Bit earthquake in 2011. But until 2015, all these kind of interference generated, let me say, in another way, using the program, using the different softwares for the processing all these kind of images and also generate the results. But after 2015, we can will live a new generation, let me say, and using the processing interference. In this case, thanks to the Copernicus program, the Sentinel-1 specifically, we can obtain information, and this new era is this possible generate in automatic way using the different algorithms and using different tools for generating in automatic way, let me say, the information related to interference for the studying earthquakes in this case. So in general way, we talk about the Sentinel-1 constellation. We have a lot of benefits using these kind of images. The first one is that we have the revisit time, let me say, the 6 days between two satellites, and we have the 12 days between the same satellite. We have a lot of images in more or less at 13 terabytes per day. We have on the special coverage more or less to 215 kilometers. We have the free and open data access of this kind of images. So we have global coverage, and then we can take account and also that this is designed specifically for these applications. So we have a high level operational service in the possible to generate different results using this kind of images. So obviously, if we have this kind of images, it is necessary to take account the development of different algorithms for the processing this kind of data. In this case, in my case, for this automatic tool, I am using the parallel Sentinel-1 DINSAR workflow. It is an algorithm developed by Manuntat and et al. In 2019. In the parallel way, the core of this algorithm is in the generating automatic in parallel way, the interference create interference mosaics, and also the generation of interference of the area of interest in this case, and also arrive to the fashion bracket. In these cases are interesting. So we have images, we have algorithms. It's important to take account that more or less we are living of the magnitude 5.5 earthquakes on the global map starting for 2013 until 2021. We experimented more or less 971 earthquakes. But if you can take account just the earthquakes that are occurring in the surface, or let me say on the land, we have experimented more or less the significant earthquakes in according in USGS and according and also in another earthquake catalog with the other service. We can more or less experimented 870 earthquakes with significant magnitude around the world. So you have this information, we have images, we have algorithms. Why is not this possible to propose the facilities to generate an automatic way, let me say, the possibility to obtain interference and loss displacement maps of the significant earthquakes around the world. In this case, we are purpose this automatic generation seismic displacement maps. This is the general workflow. We then start to extract information, specifically the earthquake catalogs, using the USGS catalog earthquake and also the Istituto Nazionale di Geofisica e Vulcanologia from here in Italy. Remember that we are working with for National Council of Research in Italy, so we are specifically studying earthquakes and also in Italian territory. In this case, we extract information related to location earthquake, magnitude, coordinates related to latitude, longitude, and depth, and also the time. The time is very important to take account just for the selected images in automatic way that I will explain after this parameter. So the first filter is the extract information related to the earthquakes. For example, for Italian territory, I'll explain before, we are working just the magnitude earthquake with 4.0 and the depth less than 20 kilometers. In the rest of the world, we have the different criteria for the select earthquakes. Just for example, we can put here the 5.5 earthquakes with magnitude and depth less than 35 kilometers. So this is the second criteria, the second filter, and after to the automatic after to select the main earthquakes, let me say the main shock, we have developed in an automatic way the query of is possible of download all that Bible Sentinel catalogs and the data download. And in this case, dependently of the magnitude earthquake, we create, let me say, in the bounding box for select all images of the Bible and the area of interest. In this case, we can select the ascendanting and descending passes of area of interest. But I explained before, this is depending of the magnitude earthquake. For example, in the past week, the earthquake magnitude of 7.4 in China, we select more or less 5-6 tracks in an automatic way. So, and all that Bible images is possible to select for start to the processing and parallel way, it created an interference of the displacement map. So after to select the images in automatic way, the tool start to the process of interference. In this case, using the parallel processing of different tracks, using the parallel Sentinel-1 DINSAR workflow that I explained before. And after this one, we can generate the interference and loss displacement maps. In this case, we are working with EPOS formats. Let me say the output data are provided according with the file standard formats defined with the H2020 European Plane Observation System EPOS project, specifically of metadata for format ISO. And we can put all this information for support and scientific community support for the experts in geophysics and non-experts, and also in civil protection that are interested in obtaining all this information. This is an example of the geoportal of EPOS. When it is possible, you can visit this page. When it is possible, select the area of interest, and automatic way you can obtain the interference. And this is, for example, an example for the interference of the past seismic crisis in Croatia in March of this year. This is the link just for the download this interference. And here you can see visit the web page for seeing all the interference and loss displacement maps and queries map, and also at violating this page. This is an example just for the EPOS project, and also it's important to take account that we have here another exploitation platform, let me say, when it's possible to obtain this information. In this case, we are using an also geohazard exploitation platform that is a JEP. So it's possible to also download all this data. So this is also unwrapping map, the loss displacement map of area of the same area. In this case, of the seismic crisis in Grecia. This is, and remember that this is the earthquake in 6.1 on in Grecia in 2021. So if we take account the working at massive information, let me say that we have a lot of images that process independently of a lot of earthquakes that I had explained before, that more or less we are experimenting 871 earthquakes. So it's necessary support using the Amazon Web Service, in this case, the cloud computing facilities. In this case, I am using the Amazon Web Service. Now it is possible the processing of generating automatic way all these earthquakes, all these maps, and put, and also in the different exploitation platform, and also in the EPOS web page. So just for introduce, we use select in the moment that we occur in the earthquake with implementing the database with different criteria selection for started in automatic way to create all the generate all the processing I explained before. And all this is implemented in Amazon Web Service when it start to generate in automatic way the different interference and area of interest depending of the magnitude, and also all this information that put in different catalogs for available and scientific community and also the civil protection during the seismic crisis. So this is just for the talk about I want to do implementation of the cloud computing. We are using the Amazon Web Service Elastic Cloud Computing infrastructure, and when it is possible, implementing all the scripts that I am working, and we put under all the storage service in S3, and it's possible to finish it all the maps that I am generating in an automatic way. So this is some experimental results. We have generated a lot of interference, so a lot of loss displacement maps in different areas of the world. We can see here different interesting results, for example, of seismic crises in the past June in 2020 in Mexico, and Oaxaca specifically, in Santa Maria Chanaydi, and also another seismic crisis in magnitude 6.5 in Nevada in the past year in May, the Pretinja, Croatia earthquake in December of the past year, another important very seismic crisis, and Grecia in November, this small earthquakes, let me say, in China, the big earthquakes in 2020, and also another big earthquake in San Pedro, Filipinas, in August of the past year. This is some results, interesting results about this catalog they are offered to a lot of users. So in general way, the conclusions, we are now on development on automatic tool that is possible to obtain the monitoring and measure and monitoring the ground generation, the formation maps of the significant earthquakes around the world. We have now an effective tool implementation when it is possible to study more or less 291 earthquakes which generate more or less 3491 to seismic interference, allow this displacement map generate that is now available in different catalog in EPOS and also JEP. So we can select this information record. All this information is available, so we can visit this web page and also extract and work with this information. We have now robust and efficient management of data and the processing on the cloud computing environment. In this case, we are using the Amazon Web Service in this for the process of this information. And we have data accessibility on scientific community with a large catalog of interference that can help to investigate on dynamic surface deformation and seismic sounds around the world. So it's possible now we can information to take account with studying of different dynamics related to the surface deformation related to the earthquakes. And also another important thing that all this information is the key element for support to the civil protection with any part of the world for during the seismic crisis. So now it's possible and also access all this kind of information in real time after to obtain the second pass of the images after the event. It's possible to also to obtain this information in real time. So This is a paper that you can see and also check in deep way this research and the global archive of considered DINSAR products obtained through InSurPace and Sentinel-1 DINSAR processing. You can see here a magazine remote sensing that is possible to check the paper and also for you are interested. And this is all. Thank you very much. I am Twitter for the consult about this, all these maps that you're generating in automatic way. So thank you very much.
Thank you, Fernando. So we are now in a question and answer session. Before moving on, let me introduce another co-chair, Marie-Pierre Doan. She is another chair.
Hello, everybody. So, we will start the questions. Do we start with the first speaker, maybe?
Yep.
A question to Andy Hooper. So, Andy, so there is a question of how do we estimate the along track velocities using burst overlaps? How do you do?
Yeah, okay. How do we actually do it? Well, we make small baseline interferograms. We correct them for the ionosphere in a time series manner. And then, of course, we made these interferograms where we preserve the burst overlap areas. So by differencing the forward-looking and the backward-looking parts in these bursts, we can get, for each interferogram, we can get an estimate of the long track motion. And then essentially we do a big inversion to estimate, so a simple linear model in time for velocity, in a nutshell. Hopefully we'll get this uploaded to a preprint server soon.
The next question is also about can you use multi-aperture interferometry to compare the results with your methods? I mean, also the bandwidth, the azimuth bandwidth is quite small for Sentinel-1 data.
Yeah, it's a good question. I mean, of course, we are using spectral diversity in the burst overlap areas. That's exactly the method we're using. But it would be possible with much smaller diversity to estimate this everywhere. We haven't tried this. I mean, of course, the measurements would be a lot more noisy. But maybe there's some merit in looking into that. Thank you. Should I go on down through the questions, or?
Yeah, maybe you can read the question and then answer. But yeah.
So there's a question from Mahmoud about how significant is the ionospheric phase in C-band compared to L-band. It's not quite such a simple question to answer. I mean, of course, in the line of sight, it's some 60 times worse in L-band, but you can actually estimate the ionospheric correction much better with the L-band. And then if you convert that to a long track, there's different diversity with the L-band ALOS data compared to C-band data. So it's hard to give a figure, but as Milan has pointed out later on, we do get very significant effects even in C-band.
Yeah,
sometimes.
Essentially, we have one reference point for each frame. So essentially, you see we process in phase 175, if I remember correctly. So each of
I can hear someone else talking, but.
And essentially, we pick it up by looking at the GNSS
a bit noisy
information we use.
Shall I carry on? A question from Sami. Do we have plans to put the long track measurements in the LIX portal? Yes, we do. Our intention is to put everything that we do to make it available online through the portal. When do I think this will happen? Yeah, I've learned not to try and predict these things. We have obviously several competing priorities in Comet. I would hope we have something operational by Lonely Planet next year. So I'll put that out there. I don't want to take all the time here.
Okay.
Yeah, maybe we can switch to question to Johan. Have you for the Aquila earthquake, you seem to have three main patches of displacement. Is it possible to use seismic source for time functions to compare with your results?
Unfortunately, I don't know what that. I didn't research enough the seismological solution or the source time function for this earthquake, so I cannot answer directly this question. But I do know that there are a few strong motion inversion with few patches of slip compared to the INSAR models available, which are much more smooth. Maybe I will continue directly to the second question, which is what will be the criteria for a good condition number. The condition number is very dependent on our problem, what the size of the fault, what the size of our data set. So there is no criteria for or a number for a good condition number because it's a problem dependent, but the condition number is getting larger as we have more dislocation in our problem, and it's getting smaller as we have more data or more relevant data. So in general, when in the iterative process, in general, the condition number is getting smaller until it's getting saturated by the data, and then it's getting larger as you add in dislocation. So in general, we're choosing this point as the optimal condition number.
Thank you. Maybe we can move to question to Feilu, and maybe if we have still time, go back to some additional question to Andy, if you agree with that.
Oh, okay, sure. The question one: could you also include a seasonal term in your model to fit in some series potential guided by GPU time series as if they are, or the time span given remains too short? Yes, we could cover. You could also include a seasonal term, but in our study we use a Gecko expression which suppresses the seasonal term. The time span, I think the 5 years is enough. Yeah. The second question, the time series processing reduce a lot the variance at distance larger than 30 kilometers, which seem important for better extracting the EQ pattern. Do you flatten the individual interference away from the EQ for time series? Is it important? I'm not quite sure about the flatten the interference. I mean, if you mean the flat space is of course is removed, or do you mean the DM error? We have tried to incorporate the DM error into the model. To be honest, it's not those that impact too much. The third question, do you think it's feasible to better locate with your approach a large number of magnitude above 5 EQ in order for the new location and depth used by seismologists to better constrain the velocity field by tomography? I'm not quite familiar with the tomography, but I think it is possible to use the better constraint location and depth for the seismology to do such things. And I think the better way to do is perhaps to do the INSAR and seismology joint inversion to determine the source location in the near future, or someone already done. Yeah, that's I answer all the questions. Thanks.
Thank you a lot. There was, I don't know if it's really a question or not, about the strong solar activity in 2015 that caused significant issues in azimuth shift. So maybe this was for Andy and Mahmoud.
Yes, I think that was more of a comment to address the question on how strong is the ionosphere in C-band. There's one other question I saw. Can you calculate the long track measurements from LIXAR products at the moment? Unfortunately not, because we don't preserve both look directions in the both overlap areas in the current LIXAR products. But yeah, hopefully, well, that will come. That will come. I think the only other question is not really concerning the presentation today, so encourage the question on GBIS and snap stamps. Like that I could encourage that person to contact me directly.
Okay.
There was a last question for Andy, I think, whether you can see seasonal along track displacement on your
Oh yeah.
Yeah, and whether you could blindly extract some along track displacement on some north-south fault or on some east-west thrust.
Yes. So no, we haven't seen in any of the examples we looked at so far. We haven't seen any seasonal variations. But yes, our intention is to blindly extract this north-south motion everywhere. Well, in all straining regions, that's our intention. So, of course, that will include along all known faults as well.
And here's a question to Fernando, and he seems to have responded, but I'm not sure if the audience can take a look at this. So please repeat this question and your answer. The question to Fernando is, have you been able to automate the phase unwrapping and quality control of phase unwrapping?
Yes. For the unwrapping phase in automatic way, the products are realized. So we don't still, in this moment, we don't have still on quality review, let me say. This is a main problem, specifically when we have a higher Fringe rate, specific of the main earthquakes. So this is in this moment we have we don't have on the still of Fringe state of the quality review of the pattern deformation of the unwrapping phase earthquakes. Mm-hmm.
So I think there's no more questions that haven't been answered.
Okay.
So I don't know. Shall we close the session now?
Okay, good. Yeah. So thank you so much for coming this session. But we have 2 more sessions on earthquake and tectonics today, and 1 more tomorrow. So please visit, please come again. And also we will have many interesting works in poster. So please visit and put your comment there. Thank you.
Thank you very much for the very nice talk.